Okay, so this one is geared towards APC and the type of material they need to cover, and anyone who's also interested in APC or the equivalent thereof. This is going to be calc-based physics, although we won't end up doing a whole lot of calculus for this particular example. But it is applying something called Gauss's law. Gauss's law, at least in equation form, looks like this. Integral of our electric field dotted with our area vector equals our Q enclosed in our surface divided by epsilon naught. Now, this one takes a little bit longer to explain. Hopefully I'll have a video concerning this sometime soon showing you what's going on here. But in short, it basically means this side is called the flux. It tells us how much of the electric field is going through a surface that we arbitrarily choose, and that is going to be directly related to the amount of charge that we have inside that surface divided by the permittivity of free space. Now, for this particular problem, I'm asking a very general question. We're going to look at a section of a conducting wire, and that wire is going to be a cylinder. Now for this, I may not have made it completely clear in the instructions, and I apologize for that, but this is just going to be a small section of a wire that continues going off in both directions. This is kind of important because otherwise, once we get close to the edges here, we'll have fringe effects, and it makes it where, technically with the mathematic tools we have, we cannot solve it. Okay? I've also said that this wire has a radius, capital R, and that it is carrying a charge, Q, equals 6Q. In other words, some random value here, that's a placeholder for whatever I'd like. This could be 3 Coulomb, it could be 2 microcoulomb, and I'd have 6 times that. Okay? It's just to get a little more familiarity with using some variables in here. Okay? Now, the only thing that has 6Q is going to be this particular section of the wire, the one that we're looking at. And then if I cut up an equal length down the way, in fact, we'll call this some length capital L for the length of wire. For every length of wire, I have about 6Q. Okay, so it's uniformly distributed there. The total charge that we have on this section that we're looking at is 6Q, and then we have a nice uniform electric field coming off of our wire. We have it coming off like that, we know, because of symmetry. We talked about this in class. We've got all of our charge gathering on the outer edge right now because this is a conductor. And so we've got them all spread out pretty evenly, which means all of the left and right that we would have from our electric field, they get canceled out. Say this guy, he'd have electric field lines that go off pointing this way, but the one next to it would counter that out pointing the same way, and we end up with a nice uniform electric field. Same thing along the bottom. I'm not going to draw all of this out. You can use your imagination. And technically, as we go around the cylinder, we have the electric field pointing out towards us and then going all the way down, and on the far side it's going all the way back in. So you can imagine which way our electric fields are going. I ask, at least at the beginning part, I want you to find the electric field as a function of little r, where r is some arbitrary distance from the center of our axis of our wire. Okay? So that r can be as small as pretty much 0 at the dead center, or go all the way out to infinity where it's completely outside the wire and really, really far away, depending on your definition of infinity. You could also go to infinitely far away if you prefer. Okay? I also note that this may be a piecewise function. In fact, many of these that you solve with Gauss's law will end up being a piecewise function. In other words, the electric field on the inside of this object is going to be different from the electric field on the outside. In fact, this leads us to our first part. So I know that I want to take a look at, for the electric field, for the region from 0 is less than or equal to little r, which is less than or equal to r. In other words, I'm starting off with some arbitrary shape a cylinder that's in here. I want to use a cylinder so that I can take advantage of the cylindrical symmetry that this problem has. So that if I have an electric field, it's going to be at a right angle with my Gaussian surface, in this case a cylinder, and it's going to be uniform across that. It'll be constant. For what we have, that's kind of what we need to do, because otherwise we need multivariable calculus. Okay, so between 0 and capital R, that means we're inside this wire. Well, inside, I already mentioned that, at least for this part, it's a conducting wire, which means this is a conductor, which means all of my charge is on the outside edge. So I would do Gauss's law. I have my electric field dotted with my area vector equals Q enclosed divided by epsilon naught. The first thing that you should draw the conclusion of is we are inside a conductor, which means, as I've told you before, our electric field must be 0. Anytime you're inside a conductor, a perfect ideal conductor, which is what we usually deal with, our electric field will be 0. And we saw with Gauss's law, as we're about to see here, that that is a natural consequence of all of our charge moving to the outer edge. Because now, with all my charge on the outer edge, up until the point where I get to actual R, I have no charge that I have enclosed. So my enclosed charge, when I'm inside of it, is going to be 0. Well, that means this whole side of the equation is 0, which means this has to be equal to 0, so our electric field has to be 0. Okay, well that was easy. So our electric field in this range from 0 to capital R is equal to 0. I guess technically this is a up to but not including. So it's a less than, not less than or equal to. Because right when we get to the outer edge, we're actually enclosing the charge that's hanging out there. So we'll take a look, and that'll be incorporated in our next portion. The next portion is to look at the outside of that cylinder. Let's go with a different color. I usually use green in class, but this time, to differentiate the two, we're going to go with red. I'm going to draw an arbitrary cylinder for my Gaussian surface. This time it's going to be outside at some distance, little r, some radius, little r. And that little r, in this case, it could go anywhere from capital R, so the very edge here, all the way out to infinitely far away. And that leads us to our next section. So we're going to look at the electric field as a function of r. This time we're going to go from r is less than or equal to little r is less than or equal to infinity. Okay? So now, I've got my region here. I've got an idea of what I'm doing with my shape, so I'm going to do my electric field dotted with my little tiny piece of area, and then I'm going to integrate this so I can get how the electric field interacts with the entire area. That'll be my flux, is equal to Q enclosed divided by epsilon naught. Well, I know that my Q enclosed, I've got all of the charge enclosed. And I said all of the charge was 6Q. So 6Q divided by epsilon naught. Okay? All right. And so we've also set it up where my electric field is constant. So that gets pulled out, and I just have the integral of dA. And that's going to be equal to 6Q divided by epsilon naught. I want to solve for my electric field. That's what I'm looking for here. Well, the integral of dA, that's just going to add up to my area, right? Okay. Well, I'll take the surface area of the outside of my cylinder. So let me get something here. You can imagine that it's like this. This is my Gaussian surface, the nice beaker here. And so I'm going to get the surface area of this, how much electric field, flux, is coming out of it. And then I can also look at what's coming out of the sides, but the electric field is pointed straight up, straight down, and straight in and out. It's always at a right angle to our vector, our area vector for the edges. The area vector for this, because it always points 90 degrees off, it's going to point straight to the left or right. And the same thing over here. That dot product, which has us take cosine of the angle between them, we end up with zero flux going through our outside edges, so we can ignore those. With most of the problems we'll be dealing with, we'll have some of the edges where we basically ignore them because they have zero flux through them. You can imagine that right here on this edge, our electric field is pointed straight out, and so none of it will be going through to the sides through this. Okay? So we need the surface area around here. Well, the surface area of a cylinder, at least the sides of it, well, that'll be the same thing as our circumference times our height, or in this case, length, however long it is. That's the surface area of the side of a cylinder. Okay, so I'm going to fill that in. I know that it's my electric field times my area, which was, I said it was our circumference, which is 2 pi r. Right now it's little r because we want the surface area of our Gaussian surface. Not big R because that's just of our wire. Right now we're outside. We could have an arbitrarily big cylinder, and so I need to use the little r, the r that we're currently at. So I've got 2 pi r, that's my circumference, times however long it is, so that's going to be capital L, equals 6q divided by epsilon naught. I find that my electric field, or at least the magnitude of it, I'm going to divide this over, is equal to 6q divided by 2 pi epsilon naught divided by RL. In other words, making this look a little bit prettier, we've got 6q over 2 pi L epsilon naught 1 over R. The important thing about this is we find that we have a 1 over r dependence. We have a linear drop-off as opposed to 1 over r squared like we would get with either a sphere or a point particle. Okay? So, the next thing that I'm going to get you set up on, but I'm not going to finish, is going to be the more complicated case where I say that, oh, made a mistake, this section of wire isn't a conductor, it's now going to be an insulator. So I'm going to have this. Still the same dimensions, still the same total charge. So we have a length of L, and we have our Q equals 6 capital Q. Except this time, our charge is uniformly distributed. That's going to take me forever to draw that out. So imagine that we've got pluses evenly distributed all around here. And for that matter, because I don't tell you anything about the Q could also be negative. It would just be negative uniformly distributed as opposed to the positive. Okay? The big difference now is, well, there are two big differences. The main thing that's going to change is now when we do the first section, from our electric field 0 is less than or equal to little r is less than or equal to or less than capital R. Now, with this not being a conductor anymore, our electric field is actually going to exist. It won't be equal to 0. And the primary reason for that is we have our charge uniformly distributed. So we will actually have charge enclosed. When I draw my Gaussian surface here, when I draw my Gaussian surface here at some distance r, maybe I shouldn't draw that right there, little r, now I need to have a way that I can keep track of how much charge I have inside this little Gaussian surface that I've drawn. Because again, I'm going to need to apply Gauss's law, which is my flux integral E dot dA equals my Q enclosed divided by epsilon naught. I need to be able to find that Q enclosed. It's not the total 6Q. That only happens when I get to the outer edge. It's going to be a fraction of that. We're going to have some of it in here. If I go about halfway out, I'll have about a quarter of the charge, if you want to do the math on that. Or if I go 3/4 out, I'm going to have most of the charge, right? If I'm really close to the center, I'm going to have very little of the charge because I have very little of the volume. This is when we need to start using the charge distributions. I mentioned, I showed you guys that we have lambda for a linear distribution. We have sigma for a distribution over an area. And we have rho for a volume, for a density, right? We're used to thinking of density as mass per unit volume, but a density can also be a charge density. It tells us how much charge we have per unit volume. In this case, that's what we want. If we can find out our charge density, then we can just multiply that by whatever the volume is that we have enclosed, and that'll tell us how much charge we have in there. Okay, so I want to find my charge density. I'm dealing with a three-dimensional object here, and it's uniformly charged across it and throughout it. So I know that my density that I want is my charge, so it's going to be Q divided by my volume, the total volume. So in this case, I know that I have a total of 6Q distributed uniformly over this entire section here, which has a radius capital R and a length L. Okay, so my total enclosed charge is 6Q, or I'm sorry, not enclosed charge, but my total charge on this section is equal to 6Q divided by my volume, so I need the volume of a cylinder. That's going to be pi capital R squared times L. That's the area of the side, the cross section, over here, multiplied by the full length. That gives me the volume of a cylinder. Okay. Hey, that's it. I found my density because I know that 6Q is uniformly distributed over this entire volume, pi capital R, because we're talking about the whole section of wire we're looking at with that length L. Now, with that, I can find that my electric field, dot dA, my flux, is equal to my charge enclosed, Q enclosed, divided by epsilon naught. And when I arbitrarily draw out my Gaussian cylinder here, in this case it's a cylinder, it isn't always, my charge enclosed is going to be nothing more than my density, rho, which I can plug this back in if need be, times the volume that I actually have enclosed, which is going to be pi little r squared times the length. That's the volume of the cylinder, the Gaussian surface cylinder, that I'm putting out there. Okay? So this is the volume that's enclosed times the charge density. That tells me the total charge that I have inside that Gaussian surface, divided by epsilon naught. Okay? Now I'm going to finish this part up for you. You can still go through and do the next part. I guess I am going to do this one for you. All right. So over here, I know that my electric field, the way we've set it up for symmetry, is constant, so it gets pulled out. We end up with our electric field times our area, which is going to be, again, 2 pi little r times L. We want to find the surface area of our Gaussian surface. So it's going to be the circumference, 2 pi little r, times the full length of it, equals, we said rho times pi little r squared L over epsilon naught. I'm going to solve for my electric field, so I've got my electric field equals rho, let's see, our pi's get canceled out, this r cancels with one of those because that was r squared, our l's cancel out, and we end up with rho times r divided by 2 epsilon naught. Now technically, rho was not one of the values that I gave you, so we want to plug back in this guy, and we will find that it is, let's see, rho is equal to 6Q divided by pi capital R squared times L. And then that's our rho, and we know that it's times R over 2 epsilon naught. Okay. Cancel that out, we're left with 3. And in the end, our final answer for the electric field inside this insulating cylinder, this wire, is going to be equal to 3Q times R divided by pi capital R squared L epsilon naught. And what we can see from this, we have our electric field is directly proportional to just our distance. So what we'll actually find is, as we move out from the central axis of our cylinder, our electric field will go proportional to how far we are from the center. At least until we reach the outer edge. Now I'll leave it to you to find the electric field outside this, because again it's piecewise. The electric field from capital R is less than or equal to little r is less than or equal to infinity. You may not have to do that much. Remember, when you get outside this cylinder, the total charge enclosed is 6Q. How does that compare to when you were outside this cylinder?